All right, what we're going to be talking about today are commonly used negative feedback amplifier topologies. The first circuit that we're going to look at is called the unity gain buffer. In a unity gain buffer, we have our op amp. I'm going to put the non-inverting terminal on bottom. And we are going to have, here's our non-inverting input terminal. Excuse me, our inverting input terminal. Down here is our non-inverting input terminal. And here is our output. Because this is a negative feedback amplifier, we're going to connect our inverting input terminal to our output terminal. And for a unity gain buffer, we do that with simply a wire. We are going to apply our input voltage Vn directly to the non-inverting input terminal. Okay. And now we're going to do our analysis to determine how this circuit behaves, and we're just going to follow those three simple steps. Okay. So that we detailed in our last class meeting. So the first step is to apply op amp rule number 1, which says that no current can flow into or out of our input terminals, and then to determine our voltage V plus. Well, in this particular circuit, it should be obvious that V plus is exactly equal to Vn, since we're applying our input voltage directly to the non-inverting input pin. For step 2, we apply op amp rule number 2. So we say that our voltage V minus is exactly equal to V plus, which in this case would simply be Vn as well. And then we apply Kirchhoff's current law at our inverting input node, right? So we're not going to write an equation for this, and I'll show you why here. If this is our current leaving the node, we have our current leaving the node in green plus 0 amps must equal to 0 amps, which means this current in green also has to be 0 amps. We can determine that by inspection, so I'm not going to bother writing down the equation. And then our last step is to solve for V out. Well, since we have a short circuit between our inverting input node and the output node, it stands to reason, quite trivially, that V out is exactly equal to V minus, which is simply Vn. So this is our input-output relationship for our unity gain buffer. The output voltage is exactly equal to the input voltage. While we're at it, we're going to define our closed loop gain. So AVCL will be V out divided by Vn, which is exactly equal to 1, which is why it's called a unity gain buffer, because it has a gain of 1. Now, you may be asking yourself, why would we design an amplifier that has a gain of 1. Unity gain buffers are used to provide isolation between subsequent stages of multi-stage op amps. So effectively, if we had a signal generator that is only capable of generating very small amounts of power, let's say that we had some sort of piezoelectric crystal, which can generate voltages rather easily, but struggles to generate sufficient amounts of current. We might use a unity gain buffer as an intermediate stage to effectively allow the sensor at the input to use the power supply of the op amp to generate currents that are needed for subsequent stages. Okay, so this unity gain buffer, what it really does is provides a very, very high level of input impedance to the sensor, and provides current through the power supply to drive subsequent stages. Okay, so we'll see unity gain buffers used a lot when we develop electronics, but with regards to actually providing any amount of amplification, it doesn't do a particularly good job because that's not its purpose. Our next circuit that we are going to look at is the non-inverting amplifier. And the schematic diagram for a non-inverting amplifier is going to look something like this. Here we have our op amp. Here is our inverting input terminal and non-inverting input terminal. So here we have V plus, here we have V minus. Here's our output pin, V out, and my power supply terminals for VCC plus and VCC minus. In this circuit, we are going to have negative feedback, and we're going to connect our negative feedback from our inverting input terminal V minus to our output V out like so. And we're going to have a resistor here in our feedback loop, which I'm going to call resistance R2. We are also going to have a resistor R1 that is connected between our our inverting input node and ground. And we are going to apply our input signal directly to the non-inverting input node. So if we apply our op amp rules, rule number 1, currents flowing in must be 0 amps. And we can see by inspection that our voltage V plus, our non-inverting input node voltage, is simply Vn. Now we're going to apply op amp rule number 2. So we can see that V minus will be equal to V plus, which is same as Vn. And we're going to apply Kirchhoff's current law at this inverting input terminal. So that's going to be adding this current directed to the left through resistor R1 and this current directed up through resistor R2 together and setting them equal to 0. So that's going to look like Vn over R1 plus Vn minus V out over R2 is equal to 0. And with a very small amount of algebra, what we will find is that our output voltage V out will be equal to 1 plus R2 over R1 times Vn. And we therefore have a closed loop voltage gain AVCL of 1 plus R2 over R1. Screen moved on me. So let's talk about the behavior of this particular amplifier for just a moment, okay? So this is a non-inverting amplifier for two reasons that really mean the same thing, okay? The first reason is that if we put a positive input voltage in, we get a positive output voltage out, right? So there is no change in the sign. So we do not invert the polarity of our signals. So it's a non-inverting amplifier. Additionally, our input signal is applied directly to the non-inverting input term. So that's another reason why it's a non-inverting amplifier. Those are really the same reason, just expressed in slightly different ways. Anytime we apply our input signal to the non-inverting input, we should see that we do not change the polarity of the output signal. Another thing to point out here is that the voltage gain, or the closed loop voltage gain of our non-inverting amplifier, will always be 1 or greater, right? So we can only provide amplification. If R2 were a short circuit and R1 were an open circuit, this would be a unity gain buffer. So a unity gain buffer is actually a specialized version of the non-inverting amplifier that is designed to provide exactly a gain of 1, okay? We'll find that non-inverting amplifiers are one of the most commonly used op-amp circuits for practical purposes. All right. This next circuit that we're going to look at is a review of what we talked about at the end of class on Monday. We're going to look at our inverting amplifier again, largely because I want to look at the differences between the inverting and non-inverting amplifier. So, as a review, our inverting amplifier has the following configuration. So it's going to look practically identical to our non-inverting amplifier. We're going to have our feedback resistor, which I'm again going to label R2. We're going to have that resistor R1 that's connected to the inverting input node. The principal difference here is that we apply our input voltage at this leg of R1 and we ground our non-inverting input terminal. I'm not going to derive this again because we did it in class on Monday. So I'm just going to give you the results. We had V out is equal to negative R2 over R1 times V in, and a closed loop voltage gain AVCL of negative R2 over R1. What I want to illustrate here is how similar these two circuits are. So I'm gonna try to get them on the screen at the same time. Might help if I zoom out slightly. All right, so these two circuits are identical except for the fact that the input signal and ground have traded places. That's literally the only difference between these two circuits. but we get very different functionality, even though there's only a subtle change in the topology, right? And it's because we're applying the input signal to the non-inverting input terminal on one and the input signal through our feedback network to the inverting input terminal on the other. So we have to be very, very careful about how we construct and design op-amp circuits, because one small change in our circuit topology can have very large effects on how the circuit itself behaves. Okay? As we mentioned at the end of our last class meeting, the inverting amplifier is able to provide both amplification, meaning it makes the magnitude of the input signal larger at the output, and attenuation, meaning it can also make input signals look smaller. So it has an extended amount of operation as compared to the non-inverting amplifier. However, the trade-off is that we also get inversion, meaning that positive input signals generate negative output voltages, and negative input signals generate positive output voltages. So we have to be very careful about which of these two types of amplifiers we're going to use, depending on our criterion that we are trying to satisfy. All right. Let me zoom back in. And I'm going to go to our next page. So here we are going to look at a modified inverting amplifier. This is going to be the weighted inverting summer. For a weighted inverting summer amplifier, we are going to have a schematic diagram that looks something like this. We are going to have our feedback resistance. And in this case, I'm going to label this feedback resistance F. Previously, I've labeled it as R2, but we're going to see that there are more than two resistors here. So that's why I'm labeling this one as RF. We are going to ground our non-inverting input terminal. So far we're having things that look extraordinarily similar to our inverting amplifier. But I'm going to include multiple resistances here. So I'm going to call this resistor R1, and at the left-hand leg of R1, we will have an input voltage V1. In the middle leg, we will have a resistance R2 and an input voltage V2. And in the bottom leg, we will have a resistance R3 and an input voltage V3. We could extend this to any number of input voltages we want just by choosing appropriate resistances R N. Okay. So let's apply our three-step process. First, we observe that our currents flowing into the input terminals must be 0. And we can see by inspection that our voltage V plus is equal to 0 volts, excuse me. Next, we apply op-amp rule number 2, which tells us that V minus must be exactly equal to V plus, and therefore we have a voltage of 0 volts at our inverting input node. And then we're going to apply Kirchhoff's current law. So I'm going to add this current plus this current plus this current plus this current together and set them equal to 0. Mathematically, that's going to be 0 minus V1, so negative V1 over R1, plus 0 minus V2, so minus V2 over R2, plus 0 minus V3, so minus V3 over R3, plus 0 minus V out, so minus V out over R sub F is equal to 0. And with a minimal amount of algebra, I can then see that V out is negative RF times V1 over R1 plus V2 over R2 plus V3 over R3. So this is a weighted inverting summer. So let's talk about why it's a summer first. Well, it's a summer because the output is has to do with the sum of the input signals. It's an inverting summer because positive input signals give us a negative output voltage indicated by the negative sign in the front of our relationship. And it's a weighted inverting summer because each of the input signals, V1, V2, and V3, get scaled by a different amount depending on the values of RF and then R1, R2, and R3. Okay, so each input signal gets scaled by a different amount, and that scaling factor is determined by the ratio of RF over the resistor associated with that input signal. If we modified our circuit very slightly, such that, so let's put this here. If R1 is equal to R2 is equal to R3, we have what's called an inverting summer. All of the inputs, V1, V2, and V3, will be scaled by the same amount. And our input-output relationship would then become V out is equal to negative RF over R1 times V1 plus V2 plus V3. Okay. So the inverting summer is a special case of the generic weighted inverting summer in which all of our resistors tied to our input signals, R1 through however many inputs we have, all have the same value. Okay. It is possible to make a weighted non-inverting summer by effectively applying multiple inputs to the non-inverting input terminal. However, the math behind doing that becomes extraordinarily difficult for more than 2 input signals. We'll kind of see why when we look at our next amplifier, but I would argue that it's much easier to design and understand a weighted inverting summer and then feed that output of that weighted inverting summer into an additional inverting stage to make the output a positive quantity than it is to design a weighted non-inverting summer. It's actually much easier to implement and design using 2 stages than it would be for a single stage. So we're not going to really address that particular circuit. All right. So our weighted inverting summer and inverting summer That's how we perform the mathematical operation of addition of signals using an op amp. Now we're going to talk about how we perform the mathematical operation of subtraction, and we're going to do that by looking at what's called a differencing amplifier. So in a differencing amplifier, we are going to have something that looks like this. It is a negative feedback amplifier, as all of the ones that we're discussing today are. So I'm going to apply a resistor between my inverting input terminal and my output terminal, and I'm just going to label this resistor R. I am going to have another resistor between my inverting input terminal R and this input signal that I'm going to call V1 here. So to this point, this looks extraordinarily similar to a inverting amplifier. Where the big change is going to come is the network that I apply to the non-inverting terminal. So I'm going to put a resistor R here and an additional resistor R here. And I'm going to apply an input signal V2 at that left-hand leg of the bottom left R. Okay. So we are actually applying an input signal through a resistor network to the non-inverting input terminal and an input signal through a slightly different resistor network into the inverting input terminal. Okay. What we have observed thus far is that when we apply an input signal to the non-inverting input terminal, we get a positive output voltage. And when we apply an input signal to the inverting input terminal, we get a negative voltage. So when we apply both, we're going to have some combination where the output is going to be associated with V2 is going to be positive, and the output associated with V1 is going to be negative. So let's figure out exactly what's going on using our three-step process. Okay. So our first step, the currents flowing into the input terminals must be 0 amps. And now we have to find our voltage V plus. Well, this is going to be a little bit more difficult than our previous examples because we actually have a resistor network that we have to take into account. So there are a couple of different ways that we can think about this. One of the most obvious ways, let's do this in pink. If our input voltage V2 is not 0, then we should expect some current to flow out of the positive polarity terminal of our input voltage V2 through this resistor R, and then it's going to see the non-inverting input node. None of the current can branch off and flow into the non-inverting input terminal, so all of the current leaving the positive polarity terminal of input voltage V2 must flow down through that second resistor R. So using voltage division, we can then see that V2 is simply, V plus is simply V2 times R over R plus R, or 1/2 V2. Now we're going to apply op amp rule number 2. So our voltage here, V minus, has to be the same as V plus So this is also a voltage of 1/2 V2. And now we're going to apply Kirchhoff's current law at our inverting input terminal. So we're going to be adding this current together plus this current together and setting them equal to 0. So our current directed to the left is going to look like 1/2 V2 minus V1 divided by R. And our current directed up is going to look like 1/2 V2 minus V out divided by R equal to 0. What I'm going to do now is just multiply both sides of our equation through by R, effectively canceling out this denominator and leaving me with 1/2 V2 minus V1 plus 1/2 V2 minus V out is equal to 0. And now I'm simply going to move V out to one side of the equal sign and group like terms together, which gives me V out is equal to V2 minus V1. So this particular configuration gives us the difference in the signals that are applied at the input terminals of the op amp. If our resistors were not all of the same value, we would wind up scaling our input signals V1 and V2. However, they would be scaled by different amounts. So I would argue that if we wanted to scale the total difference, we should then simply put the output of this differencing amplifier into an additional stage that scales the difference itself instead of scaling each individual input voltage. That would actually be easier to implement than trying to figure out how to do it using different values of R. So to this point, we have talked about how we can provide amplification of input signals, attenuation of input signals, how we can add input signals together, and how we can take the difference of input signals. We cannot perform multiplication and division of input signals using just op amps, especially not a single op amp stage. Okay, so that kind of stuff will be talked about later. But what we can do is actually apply calculus to input signals using single stage op amps. We can provide both differentiation and integration. Okay, so I'm going to go to a new page and we are going to implement both of these circuits using capacitors. It is possible to implement a differentiator, and an integrator using inductors as well. But in practice, they're usually implemented using capacitors because capacitors have a better tolerance rating when you buy a component from a manufacturer than inductors do. So you get more close to the behavior you're expecting using capacitors than if you used an inductor. Okay. So before we get into these circuits, I want to remind you guys of our relationships. The current flowing through a capacitor, IC of T, is given by the capacitance times the derivative of the voltage drop across the capacitor. And the inverse of this relationship, VC of T, is given by 1/C times the integral from -infinity to T of IC of T prime dt prime, where T prime is a dummy variable also representing time. Okay, so we need to keep those two relationships kind of in our back pocket in order for our analysis to make any sense here. Now, if I'm being honest, I tend to get these two mixed up as to which place the resistor goes and which place the capacitor goes. So I'm just going to draw one of the circuits. We're going to derive the relationship, and then I'm going to give it a name so that I don't make a mistake. So let's start with this circuit. Where here's VCC plus, here's VCC minus, here's V out, and this is going to be a time varying quantity now. Here's V plus, here's V minus. We are going to provide our feedback using a capacitor in this circuit. Actually, let me move this up slightly so I can fit in some text below it. So here is our capacitor C, and I am going to define the voltage drop across the capacitor, VC of T, to have this polarity, and the current flowing through the capacitor, IC of T, to have this direction. Down here, I'm going to have my resistor R, and I'm going to apply a time varying input signal VN on the left-hand side of R, and I'm going to ground my non-inverting input terminal. So effectively, this circuit is an inverting amplifier where we have a capacitor taking the place of resistance R2. Okay. So I'm going to apply op-amp rule number 1 and observe that no current flows into my input terminals, like so. And I can see by inspection that my voltage V plus is equal to 0 volts. Applying op-amp rule number 2, I can see that my voltage V minus, which has to be equal to V plus, is also 0 volts. And now I'm going to apply Kirchhoff's current law at my inverting input node. Okay. So I'm going to do this very slightly differently than I've done previously. I'm going to use the formulation of KCL that says the current flowing into a node is equal to the current flowing out of the node. So using that representation of KCL, I would have Vn of T divided by R is equal to IC of T. Now, we need to very slightly modify our approach again here. What we need to do is determine the relationship between VC of T and V out. Because we know that VC of T is in some way related to IC of T, and we have just determined that IC of T is related to our input voltage Vn. So how do we express V out in terms of VC? So if we do Kirchhoff's voltage law, a KVL loop here. So we're starting, let me kind of make it obvious what I'm doing here actually. So we're going to start at ground here and write a KCL equation, or excuse me, KVL equation around this path. So we start at ground and end at ground, so we're okay. All right. So starting at ground, we see our positive, or excuse me, our non-inverting input terminal, and then we have to jump across to our inverting input terminal. But our voltage constraint equation tells us that there can be no potential difference, which means we have a voltage drop of 0 when we make that jump. Then we see the positive polarity terminal of VC. So we're going to have VC of T. Then we see the positive polarity terminal of V out. So we'll have plus V out of T is equal to 0. And we can simply rearrange this to say V out is negative VC. Using this relationship, we can express negative VC of T as 1 over C times the integral of IC of T, which is where we bring in our input voltage relationship, right? So we're going to have negative 1 over C times the integral from negative infinity to T of Vn of T prime divided by R times dt prime. And since our resistance is a constant value, we can actually move it outside of our integration, giving us negative 1 over RC times the integral from negative infinity to T of Vn of T prime dt prime. So the output of this signal is a scaled version of the integral of the input signal. So this is known as an integrator or integrating amplifier. And it is a fundamental building block of multiple different aspects of electrical engineering. The integrator circuit is used in communication systems. It's used in signal processing systems, and it is used in control systems. It is also a version of an active filter as well. So this one circuit plays multiple roles in electrical engineering, depending on what aspect of electrical engineering that you're looking at. So this is a very, very versatile circuit. We will see this again over and over and over throughout our electrical engineering curriculum. The opposite of our integrator will be the differentiator. So we're going to have the exact same circuit, except that we are going to swap the placement of our resistor and capacitor. So previously, we placed a capacitor in the feedback path. So now we're going to place a resistor here, R. And we're going to place our capacitor C here. Here's our input signal, the in of T, our output signal, the out of T, and we're going to ground our non-inverting input node. I am going to call this voltage VC of T, having this particular polarity. And this current then will be IC of T. And I'm simply going to copy these relationships from up here and just move them down so that we can look at them again in a moment when we need them. All right, so let's apply our normal process to the circuit. Applying op-amp rule number 1, we observe no current can flow into or out of our input terminals. And by inspection, we see that our voltage V plus is 0 volts. Applying op-amp rule number 2, we can observe that V minus must be equal to V plus, so this is also 0 volts. And now we're going to apply Kirchhoff's current law at our inverting input node. I'm going to do it again. Current flowing in is equal to the current flowing out. And so what that's going to give us is IC of T, that's the current flowing in, is equal to 0 minus V out, so negative V out of T over R. And now I have to figure out how to relate my input signal to IC of T. So how does my input signal relate to VC of T? Well, let's look at something really quickly here. So if I draw my input voltage source like so, I can write a Kirchhoff's voltage law loop that goes from this ground through my capacitor and then down to this ground. What I will have then is negative Vn of T plus Vc of T is equal to 0. And therefore, Vc of T is just Vn of T. If I go back to my previous equation, I'm going to rearrange this slightly. So I'm going to have V out of T is equal to negative R times IC of T. And now I'm going to substitute in my relationship for IC of T in terms of VC of T. So that's going to look like negative R times C times the derivative of the capacitor voltage, where we know that the capacitor voltage is simply the input voltage. So this is going to be D dN with respect to dt. Let's write this here. And so we can see that for this particular circuit, our output voltage is a scaled version of the derivative of our input voltage. So this is a differentiator. Much like the integrator, This circuit is also a fundamental building block of numerous different types of electrical engineering quantities that we're going to be dealing with. It is also an active filter. It's used in communication systems. It's used in signal processing, and it is used extensively in control systems. Okay, so this is another one that we are going to see an awful lot throughout our classes as we progress through the electrical engineering curriculum. All right, so those are the different types of non-inverting amplifier circuits that are very widely used in a variety of industries and applications. That's all that I had prepared for today. I do want to make note that I am not available to provide a lecture on Friday as I have to attend a funeral. And so I'm going to upload a video lecture that I created last spring to cover our last topics for op amps, which is cascaded op amp circuits. Effectively, what happens when we chain multiple op amps together, which I mentioned at a few points during this lecture. We will not have a lecture on Monday either, as that's the date that your exam is due. So I'm giving you that day in this class time to work on that. The exam, I believe I have set due, is it 5 p.m. or midnight? I don't recall off the top of my head. I think it's 5 p.m. So take the weekend to work on your exam, your homework assignments and all that kind of good stuff. You also have a design project that's due fairly soon as well. It might also be Monday evening. While I will not be here for class on Friday, I will be available via email effectively all of Friday afternoon and all that kind of good stuff. Let me see what the chat says. 5 p.m. Thank you, Matthew. So if you have any questions over the weekend regarding homework assignments, your exam, your design project, by all means, reach out. I would be happy to help you. I just want to remind you that you have a lot of things that are coming due here in the next couple of days. When we resume our class meetings on Wednesday, we will begin talking about the transient analysis of RLC circuits, which is a fairly calculus heavy lecture. So I just want to give you fair warning that we're going to have to do a bit of math there. All right, if nobody has any other questions, I will see you guys on Zoom next Wednesday.